Uh, Hello everyone, I'm Dipanita, your TA for Fundamentals of Electrical Engineering. Welcome to the 10th interaction session. Sir has taught about magnetic circuits in this week. So in continuation with three-phase and magnetic circuit, we'll be solving a few problems. So the first problem today that we have is um, it's about 2 wattmeter method, like a measurement of power using 2 wattmeter method, in which it is written like the total power on a three-phase system, which is supplying a balanced load. Both the wattmeter readings are minus 12 kilowatt and 18 kilowatt respectively. So the total apparent power taken by the load is S, and the power factor is PF, and we have to calculate this power factor and S. So what is the apparent power? So if in the real power is the active power, the reactive power is what is the in terms of J, like it is the imaginary power, and the resultant is the apparent power. So if active power is, let's say, A, then the apparent power will be S A cos theta, right? So for that we need to find theta. So it is given the 2 wattmeter readings, let's say this to be P1 is minus 12 kilowatt and P2 is 18 kilowatt. Now, in the 2 wattmeter method, sir has shown like how to calculate the angle, right? Like the total power that is measured, which is the real power, which is the measurement of both the wattmeters, P1 and P2. Sir has shown it is equal to root 3 times the load voltage, the load current, cos of theta. And also like using a phasor diagram, he has shown this one, right? Like this way, where BC, these are the line voltages, and this VN, these are the sorry, these are the phase voltages. Sorry, these are the line voltages, and these are the with respect to neutral, these are the phase voltages, and this theta, like he has shown the relation with the power, so it is root 3 times um, P2 minus P1 is equal to root 3 VL IL sin theta. So sorry, yeah. So from this, the relation comes tan theta is equal to root 3 P1 plus P2, sorry, P1 minus P2, right? Uh, Let me get the eraser. So it is root 3 times P1 minus P2 by P1 plus it, whichever P2 minus P1, P2 plus P1. Let's write it in this way. So since we have P1 and P2, we can calculate theta. From that, we can calculate cos of theta, from which we can get to the uh, ap
Apparent.
apparent power, right? So could you calculate theta? Yeah. So it is. So here P2 is like 18, right? Let's just take the calculator. So P2 here is 18 and it is minus 12. So minus of minus 12, right? And this is 18 minus 12. So tan inverse of root 3 times 18 plus 12 is 30 and 6. So 5 root 3. So let's just calculate it. Tan inverse of 5 root 3.
83.41.
Sorry?
83.41 rupees.
Okay, yeah. 83.41.
Yeah.
Okay. And so the like the total P total, like which will be the real power, that is P1 plus P2, right? It is the total real power that is getting measured. So P1 is minus 12, P2 is 18. So actually the total power is 6 kilowatt. And we have theta, so we can find cos of theta. Cos of 83.41. So cos of 83.41 is 0.1147. Yeah. So we actually have the option from here itself, but let's calculate the value of S. S will be 6 cos of 83.41. 6 into 0.1147 into 6. Sorry. Like, yeah. So this is the apparent power. We have the value of S. No, the apparent power is taken by the load, which is denoted as S. So we have the value of A here. This is the real power. This is what we need to calculate as the apparent power. I'll just, sorry. I wrote this relation wrong, so it is, sorry. So let us consider this to be A, this to be, let it be B, and this is S. So A will be equal to S cos of theta, right? Since this is theta. So A will be equal to A cos theta, and B, which is the in volt ampere reactive, it will be S sin theta.
90.
Right. So so this is not correct. So it will be so we have the value of A. It is 6, this total power. So 6 equal to S cos of 83.41. So S will be equal to 6 divided by 0.1147. So, so it is 52.31.
Second option.
Yeah. So we already calculated the power factor anyway. So this is the correct answer. This is fine with you, right?
Yes.
Okay. So let's look into the next problem. Again, this is a three-phase balance load which has, now the power factor is given. It is connected to a balanced supply. The total power consumed by the load is 5 kilowatt. The power is measured by 2 wattmeter method, and the readings of the 2 wattmeter we have to find out. So basically in this case, the P1 plus P2, which will be equal to the P total, it is given as 5 kilowatt. And cos theta, which is power factor, it is given as 0.5. So we have the information, we have to calculate P1 and P2. So if we can find a relation with P1 minus P2, then we can easily calculate it. That we can get it from this theta value, right? Once we get theta, we can write it in like tan theta equal to root 3 P2 minus P1 by P2 plus P1. Then we can have a relation with P2 minus P1, and we will have two equation and two unknowns. We'll be able to calculate it. So what is the theta value from here? Cos inverse of half, right? So it is
Yes.
60 degree.
60 degrees.
Yeah. Now tan 60 is root 3, right? We have this equal to root 3 P2 minus P1 by P2 plus P1. So this can get cancelled. It is P2 plus P1 equal to P2 minus P1. So what will be the value of P1 here? 0, right? This will go away. So P1 is equal to 0. Then P2 will be equal to 5 watt, 5 kilowatt from this equation. So this is option C. It's fine, right?
Yes, ma'am.
Okay. Then let's look to the third problem. So again, a wattmeter based problem. So in this case, the wattmeter is connected in such a way that one of the current coil is connected in series with this particular phase, and each phase has a resistance of 4 ohm and a inductance of J15, right? So, and the pressure coil is connected between B and C. So there are four statements that are given, and we have to identify which one is correct. So let's read the first statement. So what does the question want? W1 measures the per phase active power consumed by the load, and the reading of W1 is something, and the reactive power consumed is something. So most of the options are actually giving the total power or the active power or the reactive power. So let us first calculate it individually and then look for which option will be the correct one. Okay, so uh, so in this phase the angle theta, like in the phasor diagram from here, I'll redraw it maybe. So these three phase voltages are 120 degree apart, right? So this is V,
Yes.
let's say. Okay, so let us start naming them. So let this be the line voltage VAN, this is VBN, VCN, right? Now this the like this angle theta here is the uh, since this is an inductive circuit, so current will lag voltage. So in this type of
Yes.
inductive circuit, current will be somewhere in this particular region, and it will be given like this. So let this angle be theta. So this will be 90 degree minus theta, and this VCN. So if we just take the like if this is 180 degree, right? So this is minus VCN. So now this angle the the in order to find the value of theta, let us first calculate theta from the resistance and the reactance. We have the imaginary part and the real part, right? So it will be theta will be equal to tan inverse of um, so this z can be written as 4 plus j15. So the imaginary part y by x, the real part. So let us calculate this first. Uh, Tan inverse of 15 by 4, 75.068
25.06.
degrees, right? Yeah. So now that we have theta, let us calculate the um, W1 reading first. Okay. So this is the wattmeter reading. So like the reactive power, like let's not name it now. Let's calculate first W1. So this will be equal to V, let's say so BC, right? So VBC, current, let it be IA. Now it will be the angle between V, this is B. So um, VAN, CN, BN, these are the sorry, these will be the uh, line voltages. The phase voltage will be sorry. The phase voltage will be, let me maybe erase this and draw it properly. So yeah, these three are the line voltages.
Yes.
Now, if like this is the
Phase
phase
voltage is common.
VBC, sorry,
Yes.
yeah,
VAN, VBN, VCN are phase voltages, right, ma'am?
yeah, these are phase voltages, and VBC is the line voltages, like from B line to C line.
Yeah. Yeah.
This is line, yeah. So in this case, the current this is just I'm drawing the mirror image of VCN minus VCN. So this is I, the current A. Now this is a star connected kind of a system, so IA, and this angle, like it is lagging with an angle of theta. So this is actually 120-degree, right? Now between these, the phase and the line, so this line voltage will lead the phase voltage by an angle of 30-degree. So basically this
Yes.
much is 90. I'll take a different color, then it will be more visible. So yeah, so this is 30-degree. So this total angle is 90-degree, because the angle between two phase voltages are 120 degrees apart, right? So between AN and BC, this will be equal to 90-degree. So since this is theta,
Yes.
this particular will be 90-degree minus theta, right?
Yes, ma'am.
So W1 reading will be cos of this angle, which is 90-degree minus theta. So in order to, like, so cos theta we can replace W1 by like this, VBC IA, cos of 90 minus theta is sin theta, right?
Yes.
Yeah. So let us, now we need to calculate, like what we are given here, line voltages, is it given? uh, so okay,
Um,
so I guess line voltage is not given here. So we have
Not
to,
there, ma'am.
okay, like in the question it was I think 240 angle 0. Maybe I for like this is 0, sorry. Maybe I forgot to write it here. So let this be 240 0. Let this be VL, line voltage. Okay. So the phase
Okay, ma'am.
voltage will be 240 by root 3.
Yes.
Yeah. So here it is BC, so we only need the line voltage. IA, we have to calculate IA. So we have Z here. Z value is given. So let us calculate Z in terms of like magnitude, and we can calculate right that, right? Or like let us first calculate the line current. Then it will be easier. So angle we have calculated for Z is 75.06, so magnitude of Z will be square root of 16 plus 225, right? Square root of 15.
7.07.
uh, uh, it's 16 plus 225 square root, right?
Yes, thank you.
Huh. So it is
15.52,
15.52, right?
Yes, ma'am.
Yeah. So IA will be 240 by root 3 into 15.52. 240 by root 3 into,
98.
yes, 8.92.
8.92.
Right. So, so VBC is actually the line to line voltage, right? So it is
Yes,
2
ma'am.
240 times 8.926. Line current and phase current will be same, and sine of theta. So sine of theta we
7.
have calculated 75.068. So into 240 into sine of 75.068.
2069 watts, ma'am. 2.69 kilowatt.
Yeah, 2070 or 2.07 kilowatt, right? This is what W1 is measuring. Now, if you have to find the total power, so the total power will be equal to uh, root 3 times what W is measuring, because here in case of three phase circuit, what is total power? Total power is 3 times of what each phase is, like each power in each of the three phases, right? Since here we are using, instead of like phase current, we are using line current. So this, like, whatever power we are getting here, it will be root 3 times of this W1. Are you getting it? So let me maybe write it in here. So see, the power in three phase system is 3 V phase I phase cos of theta in case of star connected system. Okay. So in case of star connected system, V phase equal to VL by root 3.
Yes, ma'am.
So this is equal to root 3 times VL I phase cos of theta. So this part we are calculating as W1. So the total power will
Yes.
be root 3 times of this W1, right?
Yes, ma'am.
Yeah. So let us write it. P total 2070, right? Yeah.
Yes, ma'am. Into root 3.
Into root 3.
3585.34 watts.
Something like that, right?
Yes, ma'am.
Huh. So this is the total power that has been consumed. So each phase will be divided by this 3, right? It is around, let's say around 1195, right?
Yes, ma'am.
If we just divide it by 3. Now let us look into the options. So also, oh yeah, we are yet to calculate the active power, right? We have only computed, so let us also compute the active power. So root 3, like I'm using this same relation here, right? Instead, like instead of V phase, I'm writing VL I, sorry, I phase. So it will be sine of 90 minus theta. So it will become the cos theta. So root 3 times I 240. 40 into 8.926 into cos of 75 point, what was that? 068. So if we just calculate this, so this comes out to be 956. So active here, reactive per phase, and this is the total power. So now let us read into each of the options. So measures the per phase active power consumed by the load, reading W1 equal to 319, which is not true. So we can get rid of this option. In this case, the total active power consumed by the three-phase load is approximately 356. So we got, sorry, 956. So we got this 956. The reading of W1 is approximately 2070. The total reactive power consumed by the load is 1195 units. So, is this part is not the correct option, right? Because the total power that has been consumed is actually 3585 watts, right?
Yes, ma'am.
So this is not the
Yes.
correct option. Now let's look at the third one. The per phase reactive power consumed by the load is this. Per phase is correct. The reading of W1 approximately is 2070. Okay, the reading of W1. So yeah, this one also, the reading of W1 is correct. The total active power consumed by the three-phase load is equal to 956. So active power is correct. The total in this case the total reactive power is wrong. In this case the per phase. So look at the difference between option B and C. So here per phase, if we consider, it is 1195, right? In this
Yes, ma'am.
case it is written total reactive power, which is not correct because it is 1195 is not the total one, it is actually per phase. So the option
Yes.
C is the correct one, right?
Yes, ma'am.
Did you understand the difference?
Yes, yes, ma'am. Got
Yeah.
it.
So the correct option here will be option C. If this is okay, then we'll move to the next question.
Yes, ma'am.
Yeah. So in this case, three-winding transformer is connected to an AC source voltage, as shown in this figure. The number of turns N1, N2, and N3 are given, and the magnetizing current is neglected. And in the two windings, I1 is given, and sorry, I2 and I3 are given. So what is the value of I1? You have to calculate this unknown current. So if we balance the single phase transformer, so if this one has N2 and N3 windings and this one has N1 winding, so by balancing the mmf of the single phase transformer, N1 I1 is equal to N2 I2 plus N3 I3, right? We are just balancing the mmf on both sides, and which is equal to Ni, right? So just writing this, so what we have to calculate is I1. So rest of the quantities are known, so we can simply substitute it. I1 is equal to N2 by N1 into I2 plus N3 by N1 into I3. So N2 is 200, N1 is 100, I2 is 2 angle 30 degree plus N3 is 100 by 100, this will be also 100, and I3 is 2 angle 150. So yeah, so it is 4 cos 30 plus j sin 30 plus 2 cos of 150 plus j sin 150. So yeah, cos 30 is root 3 by 2, right? 4 by 2. Sorry, this is 150. So cos 150 is minus root 3 by 2. So 2 into minus root 3 by 2 sin 150 is half. So this will be 2 root 3 by 2. So 4 by 2 is 2 plus 0.5. 5 by 2. So if we take this outside, the angle, everything is correct, right? This is plus. Sorry, yeah, this is fine, right? This will be 2 times. So it is plus j, 4. So this will be 3. Sorry, 2. And this is 1. So, sorry, it won't be 3 by 2, it will be 3. Yeah. So, hmm, we have to write now in terms of a magnitude and an angle. Let's just take out this 2 root 3. So it will be half plus. So root 3 has been taken out. This will be root 3 and 2 is outside. So it has to be by 2 j. So here this like half will be when theta is equal to 60 degree, then cos theta will be equal to half and sin theta will be equal to root 3 by 2. So basically it is if I write I1, so magnitude is 2 root 3, angle is 60 degree, which is okay, none of here, so it is option D, none of the above. Everyone followed this one?
Yes.
Okay, then we'll move to the next question. Here a magnetic circuit as shown is given where the air gaps which is denoted by Ag is given, then the magnetic core area is given as AC, so both of this are equal to 9 centimeters square. The 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 air gap distance, this is the Ag is the area of the air gap, this air gap distance is given, and the length of the flux path through the core, which is denoted by this dotted line, this is given as 30 centimeter. The number of turns of the coil is given. Assume the relative permeability of the core material is as given here. So for this specific condition, for the condition in the magnetic circuit which is operating at flux density, which is given by Bc as 1.5 Tesla, we have to find the current. So reluctance of the core is given by what it is analogous to, kind of like resistance, right? So reluctance in a magnetic circuit is given by, do you remember the relation? length by mu times area, right? So this is reluctance, right? Do you remember the relations we taught? So for the core, RC will be equal to LC, mu is equal to mu naught into mu
Mu
r,
not in
right? Relative purity and mu naught. Mu naught is constant. What is the value of mu naught in SI unit?
minus 7.
4 pi into 10 to the power minus 7. So you have mu naught into mu r into here it is AC, area of the core region. And similarly, we have a reluctance of the air gap. So let us denote by Ag, which is equal to the gap length that is given. Now, in case of gap, in place of only mu naught, right? Mu naught times the area of the air gap. And so flux is given by mmf divided by the reluctance. So mmf is equal to Ni. We saw in the previous problem, right? N times I. And the reluctance will be equal to the total reluctance of both the air gap and the core region. So we have to only find I, right? So let us calculate I. I will be equal to phi by N Rc plus Rg. This is the reluctance of both the regions. So now the we are given BC, right? So BC here, this is the flux density. So flux time divided by the area will be is equal to flux density. So we have to, since the value of phi is not given, however AC and AG are given, we can correlate it to flux density, right? So let us write now, let us reduce their expressions. So RC and RG, we can put the value LC by mu naught mu R into AC plus gap length R mu naught AG. Now both AC and AG are equal, right? It is given in the question this to be 9 centimeter square. So we can take this out of the equation. So it will be, let AC and AG will be equal to, let it be AC equal to AG equal to A. So if we take it out of the expression, phi by A times 1 by N into LC by mu naught mu R plus G by mu naught. This will be the final expression, right? Now this phi by A we can write it in terms of the flux density. So we can equate this to BC, right?
Yes.
So let us write it maybe next. Oh no, I'll write it just here. So the value of N is given. So I will be equal to 1 by N is 625. Flux density BC is given 1.5 Tesla. Length LC is given as where is LC given? Length of the core is 30 centimeter.
Big.
Yeah. So since we are writing everything as SI units, we will write 30 into 10 to the power minus 2. We'll convert it to meter. Mu naught is given. Mu naught we know is 4 pi into 10 to the power 7 minus 7.
Mu r is 70,000.
And mu r is 70,000. So 70. Okay. Plus the air gap, which is given as 0. So it is 0.05 into 10 to the power minus 2 by mu naught only, right? So 4 pi into 10 to the power minus 7, right? So just calculate this and let me know what you are getting. So we can take the constants outside. So 1.5 by 625 into 4 pi into 10 to the power minus 7, then also 10 to the power minus 2 we can take it out. This will be 30 by 70,000 plus 0.05. 30 by 70.05. Into 10 to the power minus 2, 625 into 4 to pi.
0.963.
Sorry.
0.96311. So that is 960 milliamps.
Okay. This comes out to be 0.963, right?
6311. Yes.
Okay. So it is, yeah. So it is 963.1 milliampere. So 960, it lies in this particular range, right? So option A would be the correct option. Okay. So I hope this is clear. Then
Yes.
the next problem is kind of similar. In this case, it is an iron ring of the length, mean length of 30 centimeter. It also has this air gap of 2 millimeter and a winding of 200 turns. The permeability of iron is given, which is mu r of iron. Here the current is given. What you have to find is the flux density in millitesla. So you have to find BC, which is pi by A, right? So
Yes, ma'am.
it's similar kind of a problem. So it starts with mmf by the reluctance. So yeah, you can calculate this one, right? First calculate the total reactance, which will be equal to the gap times plus the core one. In here it is the iron core. So it is Lc by, sorry, this is gap, right? What is the gap? 2 millimeter. So mu naught times area, will write as gap. Then this is Lc by mu naught mu r times area of the core. So the best, since we have to calculate the flux density anyway, let us rearrange the equation first and then start writing. So phi Ni by the Rc plus Rg. So if you simply go to the relation in terms of I, so I is equal to phi by N Rc and Rg Lc plus mu naught mu Rac plus mu naught Ag. So you have to find this quantity. Sorry, not this. In terms of radius. I mean, it has to be divided by the area, not radius. Sorry. So This is phi by n. We have the value of current. Let us take out AC and AG out, right? So, uh, like since like nothing specific is given in this question, so this area and this area, for now we are considering that only the portion which is in line with the iron core, we are taking it as A, so we'll take this A out. So basically it is uh, current is given as 2 ampere. N is given as 200 terms. So we are taking this particular term and this particular term out, AC equal to AG equal to A. Let this be A. This is what we have to find out. LC is given as, length of the core is given as 30 centimeter, right? Okay, so the length of the iron ring is given as 30 centimeter, which has a gap of 2 millimeter. Okay, please note that this is the length of the total ring that is given. So we have to subtract the air gap here to get the length of the iron core. So it is 30 centimeter minus 2 mm, that is 0.02 0.2 centimeter, right? So let us write all in meter, since anyway we have to put it in meter. So it is 0.3 meter in minus 0.002 meter. This will be the length of the core. That is the total length of the ring minus the air gap. 0.298. This is the total length of the ring. So 0.298. Again mu naught you can take it out, right? So it is 4 pi into 10 to the power minus 7. Mu r is given 1.25 into 10 to the power minus 4 plus, so length of the gap is 0.002 and the mu naught is already out. So this is equal to 2. We will write this now as flux density. So let us calculate. Okay, so yeah, we have done one small thing. So here the relative permeability of iron is not given. It is the permeability of iron that is given. So this is equal to 1. So mu naught into mu r is equal to 1.25 into 10 to the power minus 4, right? So we cannot write it here like this. Did you get it? Like the relative permeability is not given. The permeability of iron core is given. So this is a wrong thing to write. So we'll just correct it. So yeah. So it is 1 by 200 into, let us calculate this part, 0.298 by 1.25 into 10 to the power minus 4, which is 2384 plus 0.002 divided by 4 into pi into 10 to the power minus 7. This is 1591 plus 2384 divided by 200. So it is equal to BC into 19.877. So BC is 2 divided by 19.877. So 2 divided by answer. This comes out to be 0.100615 Tesla. So we have to find it in millitesla. So it is 100.615 millitesla. So this falls within the region of this option B. Is it clear? Are you guys getting it? So yeah, Bhavani, is it okay to you?
Yes,
If
ma'am.
okay, uh, if you do not have anything specific to ask, we can stop it up for today.
Nothing, ma'am. Just please update this link in the problem solving session immediately after completing this session, ma'am. That's it.
Yeah,
Last
yeah,
week's, I think you have not updated till now.
yeah. It is uploaded now. Like it was uploaded in Friday.
Okay, ma'am.
Yeah,
Actually, we don't have any problem, but still, if you have, we can check it out.
sure, sure. Okay. Thank
Thank
you for attending. We'll meet in the next interaction session.